Okay. Yeah. So just to repeat that here, what I was saying is that omega 0 and z of r are equivalent. Another give you a unique representation for the resonator. So they can be translated into L's and C's. And basically you can have the same resonant frequency by controlling L and C in different ways. Okay, so you have a choice of doing that. And what that means is that this is fixed and this is fixed. So by changing the ratio of L to C, what you're changing is C. So you now know what to do, like how to change it so that you can get larger or smaller Q. So if you want larger Q factor, you need a higher capacitance and a lower inductance, and vice versa. Which equivalently from this expression, you can see that you want, if you want Q to be larger, R is fixed, then you want the Z of R to be small, which means that capacitance has to be larger. Okay. So that makes the Z of R smaller. So this is one way of changing the Q factor when you don't have an option to change the dissipation aspect of it. But this might also not always be possible because you can't arbitrarily change the capacitance and arbitrarily change the inductance in any realistic circuit. I have mentioned this briefly a few times that, you know, these typical values of these things at microwave frequencies is not so easy to make. So again, for example, to make a very large capacitor at microwave frequencies is very hard. Even 10 picofarads as written here is quite hard for it to work, in the sense that you can of course design one, but it will not behave like a simple capacitance. It will have other associated properties which will make it look not like a capacitance. Okay, and similarly with inductances, it's often very hard to go to very large inductances. Small inductances are easy, of course. So you see that constraints what you can do with these, just playing around with L's and C's. And, you know, there could also be a situation in an experiment where these numbers are set by completely different considerations and you're now can't do anything about it. So then how do you change the Q factor? Okay, so then at least based on the simple formula, you still have only the option of changing R, but of course we can now try to make the circuit a little bit more complicated and introduce additional elements. And I think we had also briefly discussed this last time, but we will now go through it in a little bit more detail, because now R is not changeable, C is not changeable, and everything is you're sort of stuck with this. Okay. Now, having said that, I will just make a caveat, and I'll come to that in a little bit, that it is actually possible to change this, but by introducing a different circuit element, something we already know. Srijita, can you guess what I'm talking about? Like how we can make this resonator see a different dissipative impedance, which is not 50 ohms, by introducing something here.
A resistor.
Well, we already did the resistor part by introducing it here, right? So we are not talking about adding an internal dissipation. So we are still, okay, I guess I should make it more explicit. I am not trying to change the internal dissipation of this system. I still want it to be a situation where gamma internal is basically 0. And I only want to control gamma external, which in the simplest case is just 1 over RC. So if R cannot be changed and C cannot be changed, then I can't do anything, right? So I'm now talking about some other object which goes in here. So where I have put in here, which will make this guy see something which is not 50 ohm, like it's not equal to this value of resistor. We have already discussed this. So yeah, what is that? Sorry?
Capacitor.
Yes, we discussed a capacitor, and that's actually, we're going to discuss that, but something else. What am I trying to do? I want, this is a 50 ohm resistor, and I want to put something here and make it look like something else.
So then we can use a transformer.
Exactly. So we can actually use an impedance transformer and change it. But of course, there are some caveats associated with that, because remember, the impedance transformer only works at one special frequency, and it sort of works at some range. So that comes into the picture. So we'll discuss that a little bit later. We'll go to one very simple case, but since we had already discussed that, so essentially, what is the thing you're trying to control, right? If we take the example of these Fabry-Perot kind of systems which you have encountered, there it is basically related to the fact that one of this mirror is partially transmitting, right? And then you have light coming in, and then light builds up here and sort of bounces around, and then it can leak out. And how much it leaks out of here essentially is the measure of the dissipation, the sense that how much of the light is leaking out from the resonator out into the environment. And that can be controlled by controlling the transparency of this particular mirror, like how transparent it is. So more transparent, stronger the coupling, less the Q, more dissipation, and vice versa. So smaller the transparency, less light can leak out. That means less coupling to the environment, less dissipation, and higher Q factor. Okay, so a similar thing to do here is to introduce a mirror. So this kind of coupling, it's not exactly a one-to-one mapping with this picture, but it's almost like you've completely connected it to the environment. But in that case, for a Fabry-Perot resonator, if this mirror was completely transparent, there will be no resonance. So as I said, it's not an exact mapping. So what we do is we put here a capacitor.
Small question about the thing you were talking about before this. So we parameterized the resonator with the omega naught and the Z characteristic.
Yes.
And so I didn't really understand why we don't have control over the ZR and only the omega naught.
Oh no, of course. So if no, you misheard what I was saying. So of course you have control over omega naught and ZR are equivalent to defining a value of L and C. I was saying two things. One I was saying is that typically you already know this frequency, right? This is something related to whatever you're trying to do. So this is fixed. Then how to make a resonator which has a value of resonant frequency omega 0, but has different values of ZR, then you just have to change L's and C's. That's what I meant. It's not that you cannot do it.
You mentioned something about a constraint added via the port.
I added by what? Sorry?
The port being only 50, always being 50 ohms.
Because that entire discussion was based on how to change Q factor. We are still basically discussing that only, right?
Okay.
This R is 50 ohms. This you cannot change. It comes for a circuit like this, without this coupling capacitor, this is fixed. So then the only options you have to change quality factor are these two quantities. Now, of course, these are not entirely independent, but when you rewrite this turns out to be R over ZR. R is fixed. The only thing you can change is ZR. So what I was basically trying to say is that you can change ZR without changing omega naught. And that way you can tune the quality factor. Okay.
Yeah. Okay.
Is that clear to everybody? I mean, this was something I mentioned fairly early now. Any other questions? Okay. Right. So now we are trying to do the same thing where we are allowing additional circuit elements to control this. And the reason for that could be, as I said, that maybe, so omega 0 is fixed. Then in order to get different values of ZR so that you can get different values of the Q factor, you will have to change L and C quite a bit depending on what Q factor you want. And then there are practical constraints, which I mentioned, that you cannot have very large capacitances, you cannot have very large inductances. So then you don't have that much flexibility on controlling the Q. So now we are going to look at other ways of controlling the Q. And all of these are ways where you are not introducing any internal dissipation, which means that any signal which comes from the port goes back, which means the gamma, in the magnitude response of the gamma, you're not going to see any response. It's going to be flat. And the information is still going to be in the phase or the real and imaginary parts, if you want to look at it that way. We do not want the resonator or any other circuit we introduce to absorb any energy on its own. That is the sort of underlying constraint or premise we are starting with for all of these discussions. Okay, so we cannot add a resistor. Resistors are bad in general, in anything we do in our lab. But here, that is the underlying reason why, is that we basically want all the signals going in to come back out. Okay, so I then talked about the connection with the Fabry-Perot resistor, even though it's not really exact. We will come to a more exact comparison a little bit after this. So a simplest way of doing this is to add a coupling capacitor. And this coupling capacitor now acts like a mirror. So remember, the coupling capacitor is a purely reactive. So a capacitor is a purely reactive element. So it cannot absorb energy. And now by sort of getting stuck between the resistor here, which is the 50 ohm resistor, which is the source for dissipation, you have now essentially decoupled this part from this part. Why? Because any voltage which is here, so remember last time we had discussed that the voltage which is coming across this, if you call that V, then the power dissipated is basically going to be V square over 50, which is the 50 ohm. So that is the amount of power being dissipated. This is of course AC signals. So we are talking about some per unit over some average over a cycle kind of ideas, RMS and that kind of stuff. But now by introducing a reactive component here, you can now sort of see that entire voltage which is going to be here, only a very small portion of that, some V into some alpha is going to fall here, because if we choose a very small capacitor, so let's call this coupling capacitor C sub C, if C is much less than 1, then 1 over omega C is going to be much greater than 1. So, this is roughly now 2 impedances in series, even though one is real and one is imaginary, but still roughly that is so there'll be a effective current flowing through this, which will now be much smaller because the overall impedance between this point and this point has increased. And because this guy's impedance is much larger than the thing, and that you can control by making this capacitor as small as you want, most of the voltage drop is going to happen across this. And only a very tiny amount of voltage drop is going to happen across the dissipative part of the circuit, which is this 50 ohm. So for the same sort of identical conditions, you will now have much less power dissipation happening due to this resistor by introducing this coupling capacitor. Okay, is this part clear? I'm sort of trying to connect this in a way to things you might have already encountered in basic electronics. Any questions about this very basic idea, that why the capacitor has to be small? All good? Okay. All right. So this is now a way. And remember that this now completely, almost completely controls the overall dissipation, because 50 ohms is fixed. We already said that L's and C's cannot change that much. Of course, if L's and C's change, it will change the quality factor as we had discussed before. But it's going to be now a lot more easier to control, because this capacitor, you need a small capacitor to reduce the dissipation, which is usually the direction one tries to go to. One is trying to make higher quality factor resonators, which can have a very sharp resonance. So, and making small capacitors is also compatible with high frequency operation. It's easier to make smaller capacitors. So this is sort of very natural and simplest thing to do. to control the quality factor of the resonator. Again, two important points I repeat: no dissipation in the coupling capacitor. We are still in the same limit where all the dissipation is still coming because of this. All we have done is we have changed how much of this voltage drop will actually happen across that resistor. That's all we have done. Okay. Now let's look at the response of this guy in microwave office and see what happens. So we already have this angular thing set up. Let me actually, just for reference, kill this for a second so that we can freeze the previous image. All right, so this is what we had, resonant frequency close to about 5 gigahertz. Let me freeze this. I'll take this back. I've put a value of around 0.01 picofarads. I mean, I sort of know from experience what typical values here one should use if you want to do that. But this is, again, it's related to many other factors. It depends on what you have here and what you have here. Now let's see what this resonance looks like. Okay. Now this looks very strange. It seems like the resonance is actually almost completely vanished. First, the value here is now close to 0 rather than being close to 180. And it looks like it's a flat line. Though if you look closely, you'll see there's a little glitch here. Can everybody see this? Yeah. Okay. So okay. So basically what has happened is that resonance has become so sharp that it's not visible on this scale, because we are now sweeping 4 to 6 gigahertz. There's hardly 1 point it has caught here. So what we will do is, let me just increase this. So resonance has become very sharp, means Q factor is very high, which means it's very less transparent. So I'm going to make it slightly more transparent. I'm going to increase it by a factor of 10. Then look at this. And now you start to see something here. There's some feature here which kind of looks like the original feature, but it seems to be sort of coming up again close to the frequency we had originally seen it. So now we have to better zoom in to this range and see what the thing is. So we will now go back to our frequency points and set up a range here. So here I'll actually show you another trick in microwave office, which is quite handy. This here in there is the final list. This is the list of frequencies at which it simulates. So you can actually construct this list in any way you want. It could be a completely randomly ordered set of points if you like. Of course, it's not very useful because usually we're talking about frequency sweeps. But what you can do is you can have two different ranges which have different resolution, for example. So the original one was 4 to 6 gigahertz at 0.01 megahertz spacing. Let's retain that, and then let's add something here which goes from 4.9 to 5.1, and with 10 times better resolution, right? So instead of 0.01, I've got 0.01. And the important thing here is, instead of replace, you should go to add. Okay, then you hit apply, and then this new list which has been created is now added to this thing. So since this is only showing 4 to 4.1 here, you are not seeing those points. But if you now scroll up to 4.9, now you see that it is added these extra points from here. Okay, this is really just a trick in microwave office for you to know for future applications. And that's it. Now you click OK. You have to always be careful about knowing where this is. You can equivalently do the delete operation, then it will remove those points as well. Okay, by default, it is always in the replace one, so that it replaces the whole thing with this new list. Okay. So that's it. So we go press OK. Now we run this again. And now you see that it has, what did I do?
You pressed OK when it was on replace at the end.
Okay, but that should not have happened, because in fact, this is something which is a common trick which we often have to sort of learn by painful mistakes, is that you always have to hit apply in order for the list to get populated. And I thought I did not hit
Maybe
apply, so I
they
think I made a mistake.
improved it.
Yeah, I don't know if they've improved it or not, but let's see. So I'll go back and see add, apply. Okay. There you go. Okay. So now, so this is very useful when you know that you want to see a broader range as well, but you want to focus on a smaller range with finer points, so that you don't have to unnecessarily simulate too many points. I mean, for this kind of circuits, it probably doesn't make a difference because it's very little computational load, but it can be useful for other things. Now you see this thing here. Let's zoom in. So there are these zoom in tools you can use to actually see it more precisely.
Vijay, there's some electrical noise. I think it's from that charging again. Not sure.
Oh, damn. Okay. All right, let me shift my audio to the other computer. My iPad was running out of battery. Okay, is it better now?
Yeah, much better.
Sorry, hello, can you hear me?
Yes.
Yeah, okay, good. I moved my audio to the laptop. Okay. All right, so just hold on. I need to mute my iPad. Just 1 second. Yeah, okay. So you can zoom in. You can see how this curve looks like. And the thing I want you to pay attention again is, I mean, even though we are not fully seeing it, but you can see the extent of this curve here is reaching that same asymptotic value of 180 degrees, which I had mentioned for these curves to get to, right? I mean, here the resonance was so broad that even in this 4 to 6 gigahertz range, it sort of never really hit that limit. It would happen much further away. If this was a sharper resonance, you would have seen it much better. But here you see it's the same thing, but the only slight thing seems to be that somehow this curve seems to have broken up into two halves. Let's see, Joydeep, do you know why this is the case?
Yeah, so I think the phase wrapping is the issue. So we have to correct the phase, I think, the overall phase reference.
No, but what is this the same phase wrapping which we discussed in the last class?
No, so here the capacitor is adding some phase, I think, so I don't know exactly.
Exactly. So the problem is that now, remember, the reflection coefficient is with respect to this plane. This plane here, right? So this is, so we are now talking about gamma here, which now has to be a different Z. The Z is now the parallel combination of, sorry, the series combination of Z of this capacitor, which is ZC sub C, plus the Z of this resonator. Okay, again, I realize there's too many confusing symbols because I wrote Z of R for the characteristic impedance, but now this is actually really the, let me put it as ZLC, it's the impedance of this guy. So it's this Z, which will go in the formula for the reflection coefficient. Maybe I'll just call the reflection coefficient gamma R as Z minus Z naught over Z plus Z naught. Okay. And I will add this to the problem for the homework assignment. Is you will see that now the presence of this capacitors will actually introduce an additional phase shift in the overall gamma, and that is the reason why this thing has shifted out here. Okay, so what is actually happened is the overall phase has changed by 180 degrees. And then the same curve has continued. But because we define the phase typically in a minus 180 to plus 180 degree range, after reaching minus 180 degree, it has continued from plus 180 degree. So it just looks strange. There is actually a tool in Microwave Office or in other measurement tools where you can look at this, where is that now? Here. So the next to the angle, there is something called angle U. This U stands for unwrapped. Okay, so it will not restrict the phase to only plus minus 180 degrees. So you click that, and then you see that you now have the same shape. But now note the limit here. It's now starting from 0 and then going to something close to minus 360 degrees. Okay, so it is not exactly 0. This will depend on the value of the capacitor you're using. But the point is the effective shape is still more or less the same, but it's just much, much sharper there. Okay, so this is something you can use if you want to resolve this properly. So let's actually get rid of those extra points which we added, the broad one, since we don't care about those. Okay, this point is clear, right? There's no confusion about this.
Yeah.
Right. So now this is the same thing. Let me go back to unwrap so that we can look at this guy. And now all of the same ideas still apply. Okay, so let me zoom in a little bit more. So we had gone from 4.9, right? So let's go to 4.95 to 5.05. So what I mean is that the same, the plus minus 90 points, of course, now you have to shift everything by 180 degrees. So that will give you the Q factor. We can look at the real part instead. And here actually you will not be able to do the unwrap business. But what you can now see is the effect of the capacitor. As a 180 degree phase shift in the real part, normally the resonance had things going from -1 to +1 and coming back. But here now it goes from +1 to -1 and then goes back again. It looks like it could use some more resolution. Let's increase it by a factor of 10. Nice, okay. And the same for the imaginary part. It now goes the other way around. So there's overall an extra, approximately speaking, there's just an extra minus sign in the reflection coefficient of the thing, okay? But can you notice some other things here? Jay, can you tell me whether this looks identical to the resonant curves we saw earlier, where there was no coupling capacitor? Hello?
Yeah.
Yeah.
Not sure.
Let's do a comparison. I've made a duplicate where I will get rid of this. Go back to the simple case. Let's make a new graph. Okay, this was how it was before. And this is how it is now. Just to make it easier, I will just change the axis range rather than the sweep range. Why is it not? Oh. I did the same mistake. This is the new one, and this is the old one. Of course, it's inverted, but do you see something else?
It's a little asymmetric.
Mm-hmm. So here you can see that this one is not really going back, whereas over here, it has almost reached 1 here, in fact. Right, and you can see that in the imaginary part as well, because the resonance is where this crosses 0. The imaginary crosses 0 in this one directions, and they're not really symmetric about the on either side, whereas this is looks perfectly symmetric. So this is an additional feature which comes because of this coupling capacitor, right? It's an unavoidable feature. Now, one could again interpret this as an extra phase rolling, because remember that the impedance of this capacitor is not a constant, right? It's not some imaginary value which is fixed in frequency, which means that its transparency itself is changing with frequency. So when you are talking about a resonance, you usually are talking about a range of frequencies. So this has this, using of a coupling capacitor has this effect that the coupling itself to the environment is changing as a function of frequency, which then causes this kind of behavior, and an extra phase also is there. Now you can make this correction a little bit to make it look somewhat symmetric. Now I don't remember exactly, but let's try this. So remember that last time when Joydeep asked these questions about the phase wrapping, so here it's not a very large effect because the capacitor is still some small, and we're talking about small range of frequencies. But we can try to put a transmission line here and see if we can compensate. So this is sort of a unphysical thing I'm doing, but basically I'm just doing a mathematical operation using an element by introducing a unphysical filling, and that I'm going to do by introducing a negative electrical length, which is basically like cancelling off any length here. So when we do that, let me set this to 0 first. I will freeze this trace. Tuner. So let's see if this has any effect on that. So you see, you can sort of compensate for that. See, it looks, so this is at minus 0.12. So, okay, of course, that only has a meaning associated when you talk about the frequency as well, but that's okay. So now you're able to compensate this. So it's this extra phase which is changing with frequency on top of the resonance behavior, which is giving rise to this asymmetry here. And that can be compensated by this, this little additional negative electrical thing. So in fact, in the physical instruments we use for doing this gamma measurements, that what's called the vector network analyzer, this is just something you can enter and it will basically assume sort of a negative length and then just calculate that and add that phase as a function of frequency to the original response, and then you can compute it. So this way you can make the, though it has some minor effect on the location of the zeros as well, so one has to be careful about that when one is dealing with this thing. Okay, so so that's the effect of the coupling capacitor. Now, another side effect of the coupling capacitor is this.
One question. So
yeah,
here the resonant frequency has changed, or in the plot as you showed?
yes.
Or,
well, so if you notice the exact location of the crossing, that will of course depend whether you add this slope or not, right? So you have to make sure that you are in this sort of flat regime.
yes.
And only then you can choose the resonant frequency as the correct, that will be the correct one. So there is an associated point with what is the resonant frequency of the cavity when you have a coupling capacitor, which is what I'm discussing right now. So I have a very slight doubt on whether the true resonant frequency is the one after the adjustment or before the adjustment. I'm fairly confident it's after the adjustment, but I will double check this and get back to you on that. Okay, I'm fairly confident it is the one after you make it sort of look symmetric, because that additional phase rolling has a role to play here. But this coupling capacitor actually plays another role. It's not, its only job is not to control the transparency. It has an unfortunate, well, not unfortunate, but an unwanted side effect apart from this phase wrapping, which we will just check now. So yeah, okay, in fact, we can do that from here. So remember that the schematic 1 and 2 are actually identical circuits, right? So I just duplicated it. The only difference is in the whether there's a coupling capacitor or not. So this one does not have a coupling capacitor. This one has a coupling capacitor. So maybe this is actually an opportunity to introduce another concept in microwave office where you can ensure that this is always the case. So for example, so why is this? So you're trying to study the difference between adding a coupling capacitor versus not adding a coupling capacitor by having two different circuits with and without coupling capacitor. Now, this can sometimes be okay, but other times it can be slightly problematic because maybe you accidentally change something here and forget to change it there, and then it will not be identical. But is it possible to actually use a single object so that they are just embedded in different sort of boundary conditions, if you want to call them that? Okay. So one way of doing it is something called a sub-circuit. Okay, so if when you go to elements and you go all the way down here, there is this thing called sub-circuits. And by default, any schematic you make shows up here as a sub-circuit. So this is sort of like a module, you know, in a program. You write a function, it's a module, it can be reused anywhere. So it's very similar to that idea, or, you know, in the language of LabVIEW, it's a sub-VI, okay? So you can then drop this. Sorry, I've tried to drop schematic 1 into schematic 1, but let's go into schematic 1. And since this is the more fundamental object, I will take schematic 2 and drop it into schematic 1. So this box now represents this circuit, and it will have these ports existing coming out of it depending on the number of ports in this circuit. Okay, if this circuit had 5 ports, you would have a box with 5 arrows here, because those are the places where you can stick the connections. What you have to remember is that the port is just the connection. That actual 50 ohm port is not there. Okay, so that way it really works like a module. So this box is just this part of the circuit up to the from the port onwards. Okay, so what that means is that I can replace this entire object just with this sub-circuit. And this is equivalent to what I done, with the added advantage is that now if I change anything here, it will automatically be reflected in this circuit as well. Okay, this is one way of doing it, and we can just verify that nothing has changed here. This looks exactly the same as it was before. Okay, and can also show you that if I now change this guy by a small amount, let's freeze this. So small change here. Here you might unfortunately not see that change because this is a much broader curve, but basically you can see it's moving there. Okay, so this is quite useful sometimes when you're studying a more complicated circuit, which is a variation of the previous circuit, but some part is constant and you want to do that. It's very, very handy to use this. And it works for circuits with many ports as well. Okay, so this is one way. Another concept which I can talk about here is the concept of variables. Okay, so I'll put it back like this. And maybe for some reason you don't want to use sub-circuits. What you can actually use are global variables and also local variables. So one simple way of doing this would have been to not have 2 different schematics, but to have 2 different circuits in the same schematic. Though this is not always recommended that you have 2 independent circuits. From the perspective of microwave office, it doesn't really matter. It will just solve it. But now the thing is, I put another port here. And now these are 2 different circuits. It still hasn't solved the problem that I have 2 independent sets of parameters. And now we introduce the equation and variables. So there is this command here on the top right called x equal to y equation. So you can go, and you have to remember that you have to define it above the place where you're planning to use it. So this is how the, this is the rule of compilation here. I think so, but I always do this, but definitely the order has to be correct, that if there's a dependent variable, if there's an equation which is using some other variable, that has to be to the left and top of it and not below. Otherwise it will get confused. So now I can define a variable called LR and give it a value 0.1. I can define a variable CR, give it a value 10. And now here, instead of entering 0.1, I can just enter LR and CR. And then I can do the same here, LR and CR. Okay. So this now solves that problem that I don't have to worry about changing both of them if my plan is to always keep them same. The sub-circuit wrote one way, this is another way if you're doing it in the same schematic. And now you just have to make sure that you plot S22 of schematic 1 instead of S11 of schematic 1-1. Okay, that's of course obvious. These equations work exactly, they can be tuned, you can put tuners them and they will show up on your tuning curves. So you can use them the same way, but now you can reuse them in any number of positions in a given circuit. What you cannot do is something, if it is defined here, I cannot use it here, right? So if I go here and I type L of R, I try to run it, it won't like it. You see, it gave this red thing here and it gave an error here. So these are local variables, local to the schematic where they are used. But there is a way by going to global definitions and using this global definition page. Here you can define, let's call it LR global 0.1 and CR global 10. This now can be used anywhere. Okay, so let's try to use it here. Hope this works. So I recently remember I was having some problem with this. Oops. You have to be very careful. These are case sensitive, so variable names have to be written correctly. And remember that everything you define here, they have no units. These are dimensionless numbers. All the units are defined by what is set after that. Okay, it's just purely numbers. So now if I try to run this, then it's fine. Okay, so it has fun. So that way, again, you can go to global definitions, put tuners on them, and if you tune them, it will reflect across all of them. Okay, so three things: subcircuits, local variables, and global variables, which have to go in a separate location. Later on, I will also show you how you can actually define measurement equations. This thing is surprisingly powerful. You can actually define an array here. You can do all kinds of mathematical operations. There's a whole list of functions you can apply. So you can do quite a bit of computation. So maybe you have an expression for Z, and you want to compute gamma, but as a formula rather than using the S11 measurement, you can actually do that. And here, and all of these calculations are done in the complex domain, because all of these quantities are in general complex. Okay, so this is quite handy. So I will, as and when I get opportunity to introduce these kind of additional concepts for using Microwave Office, I will keep doing that. So now let's go back to the main point. So is there any doubt about this? Is okay? Any questions? Okay, just give me 1 second. Just want to have a drink of water. Okay. So, right. So we go back here. Let me get rid of this extra stuff. And I guess we can use the global definition since we've already made them. Let me kill this local ones. Back here, this looks the same. This looks the same. Okay. Now, something we sort of has been staring at us, but maybe we didn't pay careful attention, is to compare the resonant frequencies of these two different cases. Right? They are the same resonator. We only change the coupling capacitor. One has them, the other one doesn't. Let's look carefully here. Let's zoom in and put a marker at close to 0, the point where it crosses 0, and that's 5.007. This is graph 1, which is schematic 1, which is the one with the coupling capacitor. So now graph 2, schematic 2, sorry, schematic 1. I'm just zooming in so that I can, place the marker very accurately close to the. Right. Oh yeah, okay, right. Okay. So look at these values, 5.033 and 5.007. This is without coupling capacitor, and this is with coupling capacitor. Supriyo, what's going on here?
So if we draw an equivalent circuit of the full circuit, then an extra capacitance is sitting. So that C and R that can be transformed in a way so that that C comes in parallel with the LC resonator we have. So in
exactly.
Yeah.
So basically what Supriyo is saying is, this is something I would also add to the homework assignment, is to basically write this out, is that this capacitor actually has an effective capacitance which shows up in parallel with this circuit and actually loads the frequency and pulls it down. So why is it down? Because this comes in parallel, which means this capacitance adds to this capacitance. So remember, capacitors have the capacitance add when they are in parallel. So the overall capacitance goes up, and consequently the resonant frequency comes down. So this is higher and this is lower. The effect will only be very significant if this capacitor here is comparable to the capacitance here, right? Because otherwise it's going to be a small change. And usually that is the situation, because anyway you work with very small coupling capacitance because you typically want large Qs. And then here you might want to have some reasonable size capacitor, which is possible. But again, this entirely depends on the kind of circuit. Maybe you have a circuit which has a naturally very low capacitance and you cannot do anything. Then this has a much bigger effect. You can even double the capacitance, and then you have to be very careful about what will happen to the frequency. Right now, this is 10 picofarads and this is 0.1. So it has only increased by 1% in the capacitance, which means 0.5% in the frequency, because it goes as square root of the capacitance. Okay, and the specific thing which Supriyo was mentioning, and I think now I remember why he gave such an eloquent answer, is because I think I've explained this concept to him a couple of years back. Exactly. Is that right, Supriyo?
Yeah.
Yeah. Okay, good you remembered. So the trick here is to now just imagine that this circuit is basically a capacitor and a 50 ohm resistor to ground. So let's just call this R. Let's call this CC. Because we like simple LCR circuits coupled to the outside environment, without additional complications like this circuit, we can actually make an approximation and a simplification which allows us to do two things. One is this effect of frequency loading, and second is the effect of how much capacitance to put here to go from some Q value to some other Q value. In other words, what is the new expression for Q, right? I mean, originally it was R, C, omega 0, where those are related to parameters here, here, and here. But now I have this other thing. How do I introduce, how does coupling capacitor CC enter into this formula? Because we know that it will come in. It's no longer this. But can we do something so that we can write down the Q factor still in the same way, but maybe write it something like this, where you have a different value of R prime, a different value of C prime, and maybe a different value of omega naught prime, right? This is not always obvious that this would be the case. Now we know that it will be the case. So the way you do it is by writing this to be equivalent to a new circuit of this type. This is R prime, this is C prime, and then connect this to the original circuit. Now this whole thing, so remember the port is included, the port is now part of this R prime business. But since you're only interested in the quality factor, this is now a very simple circuit. The L remains the same. The C becomes C plus C prime. Okay, maybe I should call this something else. C double prime, right? So this is basically C double prime. And then there is some new value of omega prime also. And then there is an R prime. So that means Q will be R prime, omega naught prime, C double prime. So that way you can actually write down an expression for this thing. So by just, of course, these two circuits are not equivalent. So the one first approximation is that we are making an effective model like this. And the question here to ask, so now this is physics, okay, in the sense that we are now making a model and we have to justify why this is a reasonable model. Jay, can you tell me why this is a reasonable model based on what we have observed about the introduction of this coupling capacitor?
You mean replacing it with an effective?
That's right, of this type. Like there are, there could be some million other ways I could have written this equivalent circuit. Why did I choose to write it like this?
I mean, initially we chose it because we wanted a similar expression for the quality factor such that we could map.
Exactly. So that is the justification, but you can think about it in a different way, is that we know, at least from observation, that the resonance looks more or less the same, except for these phase shifts and things like that. So if everything is the same, then there should just be a new effective R here. That is the thing we were trying to target. This fact that the C is also changing and the omega is also changing is sort of a side effect which we're trying to bring in. So what we really wanted to know was that how to compute an effective R prime which can be put in parallel with the resonator so that we can use the same expression for the quality factor. Okay, so that was the original justification. So then you basically say, okay, maybe, but this capacitance, this is going to have both real and imaginary parts. And if you want to model that with another equivalent circuit, that better also have both real and imaginary parts. So if I had only put R prime, then I would have not been able to account for the imaginary part of the impedance, right? So the point is that the series RC circuit is going to have some Z of Z called, let's call it Z series. And this one is going to have something called Z parallel, which can be written as R series plus IX series. And then this can be written as R parallel plus IX parallel, if you like. And then you just equate them. And then you see what you get. There is a catch here and something, this is sort of one underlying assumption one has to make. So Joydeep, what is actually, you might already know this. So let me see, Srijita, when can I do this? Like this equivalence, obviously this is not going to work all the time. So there's something I need to assume, and I had commented about this in one of the previous lectures as well. What is one underlying assumption I'm going to make in order for this equivalent circuit to actually be valid? These are all impedances, right? Are they constant?
No, they can't be constant because XP will be omega dependent.
Exactly.
XP or XS. whatever.
In fact, we know that R, where the R comes from, and R is assumed to be omega independent anyway, that is fine. But there is no reason to assume that this R prime is going to be omega independent, right? Because you can, we already discussed this, that this R prime is representing an effective dissipation, which is coming from the transparency of the capacitor. The transparency of the capacitor depends on the frequency and the capacitance value. So then this R prime cannot be frequency dependent. So even making this matching between these two is non-trivial, because you cannot do it for all frequencies. In fact, it will not work. There will be no solution. So the assumption here is that we are saying this is a model which is local in frequency. It only works at one frequency, to be more precise. But for small change of frequencies, it's a good approximation. So we are going to say, and what is the correct frequency to use? It's the resonant frequency, right? Because we are always assuming, again, this other underlying assumptions which I've mentioned earlier, that we want this capacitance to be very small so that the frequency shift is very small, because we want high Q factors. So all of those says that the frequency is more or less going to be the same value. So I'm going to equate these two impedances, Z of S at omega 0, to be equal to Z parallel at omega 0. Okay. Only then when you do that, you will see the expressions you're going to get. So this is something you guys can work out, but I'll basically tell you what the answer is, at least for the C prime. So this is R prime and this is C prime. Turns out that C prime is the same as this, which is the coupling capacitor. This is the simplest approximation. This capacitor just shows up in parallel with the original resonator. And that is why when the capacitance adds, right? This is what I mentioned a little while back. So you'll see, and then R prime will have some expression, which will depend on, it will be slightly more expression. It will depend on the original R. It will depend on the coupling capacitor. And then you will see that by introducing a coupling capacitor, R prime is going to be greater than R, and hence Q prime is going to be greater than the original Q you had. Okay. So this gives you both the reduced dissipation effect and the shift of the frequency because of this capacitance loading. So these are, once you work this out and have these are good numbers to keep in mind, that this is a good formula, so that you can very quickly know that, okay, if this is a 10 picofarad capacitor, if I put 0.1, I don't have to worry too much about the frequency shift, but you have to keep it in mind that this is going to happen. So if we now make this 0.01, which is much, much smaller, and go to this case here, you see the frequency has shifted a lot higher. It's now close to 5.03, which is a lot closer to 5.033 than it was before. Okay, and then as you keep making it smaller and smaller, it will asymptotically approach the original unperturbed value. Okay, so again, this is a nice little problem to work out and also to keep in mind. Okay, let's see, what else did I have? Yes, okay, good. So then I will finish up this discussion by just moving to, let me just duplicate it. So in most of the things, at least from the research point of view, the kind of systems we make, they're almost always modeled best by parallel LCRs. But it's good to know the series one as well, because at least at lower frequencies, and if you have done experiments in your undergraduate laboratory on any kind of LCR circuit, it usually tends to be a series LCR. And we had discussed this in the beginning from the point of view of, what the role of the resistor is, because it's somehow counterintuitive for parallel that bigger the resistor, less the dissipation, right? So if we now go to the other situation and define a series circuit. So here's some tricks. You can right click and rotate, and then this here. Leave the R out again. Let's put this in. Okay. Let me just disable these graphs for a moment. Go back to our more broadband kind of sweep. Place. So remember that now the only thing which has changed is that the L and the C are in series. The port location has remained the same, but to complete the circuit, if I draw exactly what's going on, it's this, and then there's a resistor to ground here. Okay, so now the R is the same type of R is now in series only. Okay, it is not in parallel. It seems very strange because earlier we had said it was like this, and then we draw that, and then looks in parallel. Now this is exactly the same point, but now it looks in series. But I hope this makes sense to you what I mean by that. It's series here because the same current flows through exactly all the three devices, right? That's how we think about this. Okay, great. So now if I look at reflection coefficient and the associated properties, it's going to be different because the Z of LC is now going to be the series combinations of L and C. So it's going to be like J omega L plus, minus J over omega C, right? Whereas earlier it was the parallel combination of these two. So that means gamma will be different because ZL is different. So you're going to measure reflection coefficient from this point of view. So, however, you must remember that the resonant frequency of a series LC and a parallel LC are actually the same. They're still given by the same formula, 1 over square root of LC, right? Now let's see what happens here. We'll plot gamma. I'm going to make a new graph. Let's call it first. Let's convince ourselves again that there will be no magnitude response because the series LC circuit is also dissipation free. Always remember to choose the correct data source here. S11, there's only one port, and this thing, boom, it's 1. Okay, so no problem there. As expected, no dissipation. Let's go to angle, and oops, what did I do? Oh, yeah. Okay, looks very strange. Looks like it's inverted. Something is going on, but one can barely see any width. It almost looks like it's going instantaneously. Let's look at some other versions. Let's look at real part. Wow, this looks really bizarre. Maybe let's add imaginary part as well to this. And thing looks really, really strange. Okay, now it looks very strange, but what are the things which look okay in the sense of how the previous resonance used to be. So in fact, let me enable this one.
It's crossing 0 at the correct point, imaginary point.
Exactly. So remember the standard parallel LCR, the real part went from -1 to +1 and reached +1 at the resonant frequency. And the imaginary part crosses 0 at the resonant frequency. Now, if you look at this guy, you do see that there is some crossing 0 of the imaginary part, because this is 0 here. Sorry, one second. Excuse me. All right. And the real part seems to be stuck at 1, but it does seem to reach 1 exactly at the same frequency where this reaches 0. Okay, so in that sense, it's similar to this. So maybe we can believe that this is the resonant frequency. But Jay, what is your guess of what has happened here?
So the resonance is extremely broad, which we sort of changed that in the previous case, and we could make the resonance sharper and broader. So we sort of maybe hit the other extreme of that same thing.
I have now swept from 1 to 20 gigahertz, but maybe that's not such a good idea because we know the resonance is somewhere around 5. So let's keep it reasonably symmetric. So that would be 1 to 9. Okay. It still doesn't look very familiar to what we know. It's like not even coming back. But exactly what Jay is saying is correct. There was no reason to expect. We use the same L, we use the same C, which meant the resonant frequency was supposed to be the same. We also use the same R. But however, what we discussed earlier about dissipation is now a whole different ball game, right? Because now the relevant dissipation term is I square R and not V square over R. Because the defining quantity here is the current through this thing is what goes through the 50 ohm resistor. So now larger the resistor, much more is the dissipation. Okay. So we will do something unphysical, which in the sense that we can't do that in a real circuit. But just to see, I will change the port impedance, which I'm allowed to do in microwave office, can't do in the real system. And I'm going to decrease it. Right? And it's starting to look somewhat okay, but not really. The shapes are not really familiar. Now it's starting to look familiar, right? Now I'm at a value of port impedance of 1 ohm, and I'm still very, very broad, right? Remember, I'm sweeping from 1 to 9 gigahertz now. So the bandwidth is something like, going from 4.3 to 5.89. So it's huge bandwidth. And this is because this is a completely sort of a dual situation where even the slightest amount of resistance is very, very bad for the dissipation point of view. So if I go to even lower impedances, then you get the more familiar looking situation. Okay. Now this looks exactly like what we knew. The phase is reversed. Here it goes from -1 to +1. Here it goes from +1 to -1. That's again because of the nature of the gamma expression is going to be different. This again you can check in your homework. So what this tells you is that if you have no control over your source impedance, in reality 50 ohm, then it's a terrible idea to make a series LC circuit, because you're going to get very, very low quality factor. Now, having said that, there is, of course, you can choose L's and C's, just like you had in the case of the parallel circuit. Remember, Q also had this expression, which was R over Z of R, where Z of R was square root of L over C. This is for Q parallel, okay? I'm going to give you the result for Q series. It's actually ZR over R. This is exactly the inverse of that. Still a dimensionless number, but now the dependence on R is 1 over R, which means that you could, in principle, increase Q if R is fixed by making Z of R very large. But remember that R is 50 ohms. And if you want, high Q means at least like few tens or few hundreds. Normally we're talking about hundreds and thousands, which would mean that you would need Z of R to be 100 times 50 ohms or 1000 times 50 ohms or 1,000,000 times 50 ohms. Now that is just impossible to design in a microwave circuit, because that means that L has to be very, very large, and such large inductance are just not possible using conventional geometric circuits. Okay, so it becomes very hard to get the quality factor in this kind of a geometry. So in any case, we usually don't make lumped element resonators at microwave frequencies. Typically we use transmission line based resonators, and that will be the subject of the next lecture, where we'll continue with resonators, but now we will move to figuring out how to make them using sections of transmission line. This is basically the more closer analog to the Fabry-Perot type of things, where you have a medium where light can travel and you put two mirrors on either side. And again, those mirrors could be capacitors or other things, which I'll discuss next time. Okay, so this was just to sort of complete the story of parallel versus series. Remember again that all of this constraint is coming from the fact that we have to work at these high frequencies, where the characteristic impedance of your transmission line and the ports cannot be very different from 50 ohms. Also, value of L and C have to be within a typical range for them to behave properly. And that is the constraint. However, at room temperature, not room temperature, at very low frequencies, these constraints don't matter. You don't have 50 ohm sources. You can have a source with a very, very low source resistance, because an ideal voltage source has zero source resistance, and such sources do exist at low frequencies of kilohertz. And these are the kind of things you use in your lab experiments. And then you can make largish inductances as well at low frequencies without any problem. Just have to keep winding more and more wire. And again, the reason that it works at lower frequencies is what we discussed one of the first lectures about, the wavelength. At such low frequencies of kilohertz versus gigahertz, you're talking about 10 to the 6 difference in the wavelength. So the wavelength at kilohertz frequencies is like, huge. So everything looks like a lumped element. You don't have to worry about the fact that your inductor is now, the size of a lunchbox. It's perfectly fine. The phase is uniform across the entire inductor. There's no problem in getting it to work. It will have some resistance, fine, but that resistance will also be small compared to the L in the kind of Cs you can get. So you can make series LCR circuits at lower frequencies, but at lower frequencies, you don't talk about gamma, because it doesn't make sense to talk about waves traveling back and forth because the wavelength is so huge. So you talk about more in terms of currents and voltages through the inductor, across the capacitor. Okay, so this is another example to sort of contrast between what is happening at low frequencies versus high frequencies. Okay, so let me stop there and I'll take some questions and then we can end this lecture. All right, any questions?
So in the previous situation, we could sort of improve the quality factor by adding a capacitor in series by changing the voltage difference.
Yes.
So here, since it's not voltage anymore, it's the current which is traveling through the resistance which matters. So the equivalent of that be something like adding a inductor in parallel or something like that.
Yes, that is a very good question. In fact, I have, just as you were saying it, I was trying to think about what the answer would be. So it's obvious that it cannot be in series, right? Because if you put something in series, it's going to become part of the resonance circuit and actually completely modify. But it is possible to put it in parallel. However, that might also have a much bigger loading effect. There's actually another way of doing this, which might be a lot more practical. It involves a slightly different version of components we have discussed so far. I mean, we have not considered this. Can someone tell me? So what Jay is suggesting is that maybe, you know, if you put something here to the ground, it's probably okay, right? Because what is actually happening? So what is the requirement here, right? So this is, so let's replace this with our usual resistor. What we want is that the current which is flowing here does not dissipate through this thing. Just like in the parallel case, we did not want the voltage drop here to appear entirely across this one. So for that, we chose this to be a very high impedance. So that reduced the voltage drop here. In exactly the same way here, because it's the current we are worrying about here, we want the current not to flow through this. So it's perfectly okay to imagine something here. So if this current, let's call this I shunt, has to be much, much greater than IR, which is the current through the resistor R, then what it means is that this shunt has to be a very low impedance object. So it needs to be reactive and low impedance. So what is a good object to put there, Jay, since you introduced this?
If it's low, then probably capacitance.
Capacitance is low inductance?
Oh, no, sorry, it's the reciprocal. Yeah, sorry, the inductor, yeah.
Well, of course, you can make a capacitor also low impedance by making the capacitance very, very large, but large capacitors are hard, right?
Yeah,
but in principle, yes. So you put here now an inductor, right? So L shunt, maybe just erase everything. L shunt has to be much, much less than 1. This actually solves all kinds of purposes, right? Basically, this is like a short circuit. 2, which means that most of the current will flow here and not through the resistor, which is in parallel here. So the true condition is that omega Ls should be much, much less than R. Right? That's the condition you want. Where omega is basically again omega naught, the frequency at which you are going to resonate. 2, if Ls is very small, you look at this circuit. This is now the new circuit, right? So it's very nice, actually, dual of the other case. What is the resonant frequency of this circuit? Capacitor is the same, but now the inductance has become L resonator plus Ls. So it's going to again move the frequency a little bit lower. But if Ls is much, much smaller than Lr, then that shift will be very small. Okay. So in fact, since we looked at this, why don't we actually see this in action right here? So I've actually never worked through this, but this is very cool. By the way, you can do the same thing even in the case of parallel case. You can put an inductor in series as well if you want. You just have to make a very large inductor in that case to get the same kind of impedance. So let's take the inductor, short this to ground, and this was what, 0.1 nanohenry. So let's make it 100 times smaller. So 0.001. Look at this.
You scale the same variable in that when you are defining the inductance?
Yes,
you
can use an equation here. Yes, you can actually say 0.01 into LRG. Absolutely. Good. You can do that. You can also define another variable with that expression and then put that in here if you want as well. But this is allowed. And let's look at this guy. And of course, now the resonance has become so sharp. I was looking at a very broad range. So let me zoom in again. Remember, it's going to be close to the same range of values. In fact, I've made it too sharp. So let's back down a little bit. All right. So now you can see. So again, it's lower than 5 gigahertz because of the same kind of loading effect. Now it's the inductor adding to the inductor as opposed to the capacitor adding to the capacitor. So it's a very nicely dual thing. Capacitors become inductors, and inductors become capacitors. So now you can see the shape is again very similar. It's just there's an overall phase shift again because of the same kind of situation. So the real part is going from -1 to +1. The imaginary part goes in the other direction, but it's perfectly fine. Okay, great. Yeah, that was a good question to ask. But there is another actually way you can do it, which I guess effectively is doing the same idea, but and it's a lot harder to do it in microwave frequencies. But you could replace the this inductor with actually a mutual inductance. And this way you can control the coupling by also controlling the M here a little bit. But I don't think it buys you anything necessarily than the simple trick, which already we, but this is another way one can do it. And there are actually some scenarios where people use this kind of an effect in real experiments. I'll point that out when we discuss that. Okay, any other questions? All right, good. So let's end there, and I will send you. Hey, Jay, can you send me a reminder later tonight if I don't send this homework question there? But I'll try to do that within the next hour.
Okay, so okay. Maybe around 11.
Yeah, that would be great. Okay, all right. See you guys next time. I will check your schedules. So I know all of your stuff. Supriyo, you're not taking classes anymore, right? Yeah, okay, fine. So I'll check your timetables again and come up with a second slot to start with so that we can have 2 lectures a week from now on. Okay. Okay. All right. So good night, everyone.
Yeah.
Bye.
Bye.